We need to determine the, I think, stiffness coefficients or flexibility coefficient. I mean, geometrical and physical interpretation of the, I mean, through sketch. We don't have to write any formulas or any quantities. It is just the physical interpretation of the truss. So I am drawing this truss here. It was this kind of arrangement. Okay, now this truss is being supported at two ends, let's say 1 and 2. Now there are two joints given which are pin connected. Of course, all the members of the trusses are pin connected joints. Now we want to understand the physical interpretation. What is the meaning of physical interpretation? To understand the physics or to understand the mechanics, what's going on inside, and through the concept of stiffness and flexibility. Physical interpretation of the system through the concept of stiffness and flexibility. So we have to determine the coefficients. The flexibility and stiffness coefficients, all of you know, we have named it the flexibility coefficient as F and stiffness coefficient as S. But it all depends on how many kinematic degrees of indeterminacy. In this case, in stiffness case, and in flexibility case, how many how many static degrees of indeterminacy in the structure. So the concept was very simple, that if we want to get the stiffness coefficient, it is nothing but the force due to the unit applied displacement or unit applied rotation, depends on what kind of problems we are dealing with. Suppose we are dealing with beams, their deflections as well as rotations can be your kinematic variables. Here we are dealing with trusses. So your kinematic variables may be horizontal translation or vertical translation. In case of trusses, horizontal translation or vertical translation. So in this truss, these 1 and 2 are supported. Now there are two more joints, and we are writing our kinematic variables or static variables. Both we are writing only at the joints. It is being written only at the joints. We are not concerned what is happening away from the joints. So in this truss, let's say 1, 2, 3, 4. Now all of you know that 3 and 4 can have the kinematic, it can have, joint 3 can have horizontal and vertical translation. Assuming there is always a load, either horizontal or vertical. But since we are going to write only physical interpretation of the stiffness and flexibility coefficients, so we will have our own interpretations of applying the unit load or applying the unit displacements. Here in this diagram there are, I think there is a load which is shown. The external load is given is just the concept. Here the external load is given A1 here, then A2 here. If you look at the exercise, you can check A3 here and A4 here. There are 4 external loads are given. But while calculating stiffness and flexibility coefficient, we are not going to actually include these flexibility or stiffness coefficients. Sorry, we are not going to include the load. Effect of the load is not required. We are calling that ADL matrix. When we solve the in example for truss, we will able to know that under the external load, whatever the stiffness coefficients are generated or flexibility coefficients are generated, we are naming it ADL. In case of stiffness method, we have learned ADL. So here we don't want to write ADL matrix, it is not required. We want to write only the physical interpretation of the stiffness and flexibility coefficients, and that we will be able to obtain only by either applying unit load or applying unit displacement. So one by in this case, okay, coming back to this, joint 3 can have horizontal and vertical translation. Joint 4 can also have horizontal and vertical translation. So now we have to see how you can obtain. It is just the sketch that we need to draw here, because some students have tried, some are still not able to understand. If you are able to understand this, you can understand everything, but it depends on what kind of problem you are dealing with. So I am again drawing this sketch where this truss is having 4 kinematic indeterminacy. Okay, so on this joint 1 or 2, now I am renaming the joints, numbering. To obtain first job, let us obtain flexibility coefficient. So let us pick up joint 1. To obtain flexibility coefficient, we have to pick up joint 1 by 1. On joint 1, how many kinematic, how can we obtain flexibility coefficient? By applying, it is the coefficient because of unit load. We have to apply unit load or unit force at joint 1, 1 by 1. Please understand, there are 4 loads, A1, A2, A3, A4. So out of these 4, we will apply unit load 1 by 1 and let other 0. In second case, we will apply 0, 1, 0, 0. Then we will apply, in third case, we will pick up second joint and we will apply load 3 as unit, and rest of the load are 0. And fourth case, we will apply fourth load as unit. Please understand, these 4 loadings are given, and those are acting at the joints. So when loading is given acting at the joints, if it is not given, because we are going to calculate the corresponding displacement or corresponding flexibility coefficients according to these loads. Even if those are not given, we can imagine the flexibility coefficient by applying unit load. Even if the loadings are not given, you can imagine there should be unit force here in this horizontal direction, there should be unit force here in vertical direction, there should be unit force or there should be uniform. To get flexibility, even if there is no load given, you have to understand this is how I can apply the unit load and to get the flexibility coefficient. So what I am suggesting is, now we will apply 1 by 1 the first case, that is the horizontal load should be unit. So what I do is remove everything now, just apply unit load here in this direction. unit value. And if you apply unit force here, your deformed shape will be something. Let us assume it will be, let's say I have applied, because it is a integrated system, all other members are also joined. Let us imagine a diagram where I can have this geometry deform. I mean the deformed shape of the truss. Because I am applying unit load here, I am assuming okay this joint will displace here, and we want to calculate this displacement, as well as if this joint is not likely to displace, you will not get flexibility coefficients. Assuming if I am pulling this joint, please understand I am pulling this joint with the unit load. Let me redraw so that it is more clear. I am applying unit load here. Now if you pull this joint, because the system of the truss is such that it may deform this way, something like this. It may have vertical as well as horizontal translation. So that vertical translation and horizontal translation away from the joint. If this is the joint, original joint, and this is a final displaced position, I can see why, don't think this can translate only horizontal under this unit load, because the system is such that it may translate vertically also. That is our assumption, that this joint will deflect vertical as well as horizontal. Now to get flexibility coefficient, it is nothing but if I calculate horizontal displacement, if this joint has displaced vertically, so this will be your vertical displacement, but from here to here it will be horizontal displacement. So that horizontal displaced coefficient, what should I call? Let us call F11. It is as simple as that. And vertical translation, let us call F21, because we have applied unit load at joint 1 in horizontal direction, that is A1 is equal to 1, and that numbering I can, horizontal direction load, that numbering A1 is equal to 1, I can name it 1, in the horizontal direction. So this becomes F11, F2. Now assuming okay this has not displaced, this joint was undergoing the load, unit load, but this joint was not undergoing any kind of load. So these are the pin connected members, and then system is such that this will not displace, because only this, we are pulling only this joint in horizontal direction, because if I pull vertically then this will displace, but if I pull horizontal, see it is, you have to intuitively imagine, you have to do some experiment physically. Okay, if I pull this joint will not displace, please understand, this joint will not displace. So F31 and F41, please correct me if I am wrong. F31 and F41, because we have applied unit displacement at 1, and this we are calculating at 3 and 4. This is our joint, 3 and 4. This is just the numbering, horizontal displacement and vertical displacement. Here 1 and 2 will be horizontal, 1 and 2 will be vertical direction. So F41 and F31 should be 0. Now, now we will apply at A2 is equal to 1 in vertical direction. So how our shape will look like? So in this case only this much information was required according to your exercise, the example given. Only this much. Only you have to draw the diagram and just write the flexibility coefficient. So next diagram I am pulling the joint. This was our original. Let us pull this joint now. A2 is equal to 1. Upward direction. Now if you pull this upward direction, this will have a shape like, if you pull this up, it will be somewhere here. Because this will also go up at the same time. The whole thing will go up. So it will be something like, new shape will be something like this. This joint will also go up. And I can, this is support, so I can join now this. Because I am pulling it upward. You can little bit extend it. Okay, when I am pulling it upward, it will pull, but because of the integrated system, it will, assuming there will be horizontal and vertical translation. Because this member is also connected with other members. So if you pull this, it might happen that there will be horizontal and vertical translation for the new joint also. And here also there will be horizontal and vertical translation. So in this case what we do is, we write our flexibility coefficient. There will be, this will be the vertical translation, and from here to here, from this joint to this, just you have to measure the horizontal displacement, nothing else. Just measure the vertical. In reality, if it is 0, then it can be 0. But assuming it is being displaced, we don't know what kind of displacement that will arise. This is just a concept. Please understand. Here, because we are pulling it this way, intuitively we can understand, okay, this can be 0, the horizontal end. But here it may not be so. If we are pulling it up, even this joint will be going up, and this joint may also translate horizontally, going up as well as going, it can undergo horizontal translation as well as it can undergo vertical translation. So this coefficient we name it simply because we are going to calculate now f, we are this horizontal translation will be f12, because we are calculating displacement at 1 and calculating, it is unit load is applied at second place, that is in vertical direction. So F12, and here we may call it F22. Similarly here horizontal translation we can call it F32, and then vertical will be F42. That is all, only this much. For the first joint we have applied A1 as 1, A2 as 1. Now let us consider the third case. What we will do in third case? What we are going to do in third case? See, we have obtained, yes, very good. So one student has answered me that you want to apply now A3 is equal to 1. So we will apply A3 is equal to unit load to get the flexibility coefficients everywhere else. So your diagram will look like something. If I pull this, I will draw the diagram here itself in this picture. Just hypothetical thing, please understand. Hypothetical idea that I am pulling this joint in the horizontal direction. It will be like this. Even this may translate horizontal or vertical. Assuming it will be there. I don't know what is given in the answer. I don't know whether they have given zero coefficient here, vertical or horizontal, because see, I don't know. Actually, I have to. All of you have gone through theory of structure course and virtual work principle, energy principle, where in the trusses we have calculated displacements at every joint. So only after calculation we will come to know, depending on the what loading condition, magnitude of the loading, I can come to know that this joint will displace or not displace. So we are assuming if you pull it horizontally, horizontal may, there is one possibility that it might displace in horizontal direction. So your F33, this will be your F33, and F43, let us assume 0, because we are pulling this joint horizontally. How can it be displaced vertically? This is how. So F33 will be there some value, but it will be horizontal direction, and F43 can be 0. So 0 and non-zero quantity that we are writing. Now if I have the horizontal displacement here as well, I can call F13, F13, and then vertical direction, if there is a coefficient, let us name F23, something like this. Now next diagram will be the last one. We have to make A4 is equal to 0, sorry, 1. So we will pull this joint vertically. This joint will be pulled vertically. This joint we have to pull it vertically. Okay, I understood that you have been confused with this example because you were not knowing which direction the displacement has happened. But this is just the interpretation and concept. You can imagine that there will be displacement, there may not be displacement. So I will pull now this joint. and the displaced position I am showing here. This was the original truss. Something like this. This was the original one, and then when you are pulling it, this was a new position that we have got. If you are pulling it up, A4 is equal to 1. I think if you are totally applying vertical force, it should displace only vertically and not horizontally. That is my assumption. So whatever I am showing here may not be true. You can put your joint somewhere here. It is displacing in vertical direction. It is very logical that if you pull up, there will only be vertical displacement. It is as simple as that. Just like we have shown that if you pull horizontal, you will have only the horizontal displacement. So anyway, I think you may assume, okay, there are all coefficients are there. There will be displacement in horizontal, vertical direction both. Then we may name it, vertical and horizontal. Then you name just the stiffness. Assume that, okay, there are displacements. Displacement will happen in every situation. Then, okay, it's okay if you don't write any coefficient 0. But this is quite logical, and I understand without calculation how do we know that it is 0, because you have to do some experiment, that if you are pulling this, whether really it will deflect or not deflect, because the arrangement of the truss system is like this. It's a bit complex, that's why. So if I am pulling up and there will be horizontal vertical translations, then let me call this as F44, sorry, F4, F34, and let me call the vertical translation, this is a horizontal, vertical translation as F44, and here I may call it, if it is horizontal, F14, and here vertical, let us call F24. You just have to look at the subscript 4 here, 4, 4 and 4, and just 1, 2, 3, 4. So this is about flexibility coefficients. Now we have to do something about stiffness. So stiffness, what we will do, we will apply unit translation. So if you apply unit translation at joint 1, let's see. ये जो joint है, you are pulling this joint. Not pulling it, you are allowing displacement, this joint to displace at value 1. Now we are generating stiffness coefficients. So if you are pulling this joint, our shape will become like this. But now in stiffness, now our job is to calculate the forces at 1 and 2. So let us name one by one. Simple. This will be S11, obviously. Vertical force, horizontal and vertical force. I'm not showing a reaction. You can show reaction because now there will be a force. You may show this hinge here. Here also you may show hinge. Last in previous classes I told you that you have to imagine the virtual support to have the forces generated because of this unit displacement occurring at joint 1. There will be two forces here and two forces here. So one we are calling S11, second we are calling S21, because we have one says we have translated this joint 1, horizontal in horizontal direction. So this will be S31 horizontal force and S41. Similarly, we pull this joint upward. So let us pull this joint upward. Again we have, if you are pulling this upward, the original truss was like this. Sorry, it was just the horizontal. So original truss was like this, and this was the final deformed shape. So there we are allowing unit displacement in vertical direction of this joint 1. So there will be two forces here, one vertical and one horizontal. Again you can introduce support here and again introduce support here. Because of vertical translation here of joint 1, there will be four forces generated at joint 1 and 2 both. There will be horizontal and vertical force. So let us name it S1 2, S2 2, S3 2 and S4 2. Don't mix up any subscript. Now we have done so much exercise that you have to remember these symbols. There shouldn't be any confusion. Similarly, we will do the remaining two cases. We want to apply unit translation for joint 2, both in vertical and horizontal direction, to get the stiffness matrix. So the third one will be, this joint will remain as it is. Now we want to translate this with unit value. Translate horizontal joint. So if you translate it, the new position will be like this. So this was the original one. This was the original, but this was the final one.